Do you like to work with metal, fire, electricity? Would you like to make money doing it? At Southwestern, we can help make your dream a reality. With our degree and certificate programs in welding, you'll be prepared for a career in the welding and fabrication industry in as little as a year. Check out our website and let Southwestern spark your career in welding today.
This is Southwestern's dental assisting program. In just one short year, you could be a dental assistant. Sign up now for your one-year dental assisting certification.
Hi, my name is Ron Metzger and I've been teaching geology at Southwestern Oregon Community College for the last 20 years. It's an exciting time to be teaching in the health and science fields at SWOCC as we work towards funding a new health and science facility at the college. Colito Hall is the building I work in and it houses our science labs. It was constructed in 1965 and the labs have undergone relatively little updating since that time. Over the years, we faculty have provided an exceptional foundation in the lab sciences. It's relatively easy to see how an investment in the health side of the facility will pay dividends in our local communities. The added lab and class space will allow additional cohorts of nursing students and new programs. This will allow our local residents to go through the programs and earn family wage jobs at Bay Area Hospital and all of our other local healthcare providers. As we look forward, it'll be interesting to see what we accomplish as a college and community with lab facilities and equipment equal to the task of teaching in the 21st century. I hope you will work with me as we move forward with this project.
tells any jokes at these things. And he goes, well, you know, Roman, the deal is if the jokes are projected on the screen right now, you're not allowed to laugh at them right now. So that being said, please refrain from laughing at any of the jokes you see on the screen. So here we are. We're going to talk about magnetic reconnection. And to give you an idea of what we'll talk about first, before we talk about magnetic reconnection, we have to talk about plasma. And so I'll give you a crash course in plasma physics. Then we'll discuss a little bit of magnetic reconnection. And then I'm going to talk about the project, specifically the instrument upon which I've worked, because it's the way we parse the plasma. You know, I teach astronomy in San Antonio, Texas. And one of the things I always try to point out is that the most amazing things that are happening out in the universe, you can't see with the naked eye. You know, we can't see X-ray flares or anything like that. You've got to build specific instrumentation to be able to resolve that. And the same thing goes with plasmas. You can't see plasmas. So you've got to find ways to, in quote unquote, look at them. And I'll talk about that. And then I'm going to talk a little bit about the place that was crazy enough to hire me, Southwest Research Institute in San Antonio. It's a wonderful place to work, top-notch research facility, and we have a lot of things that we do. So I'll kind of give you an overview of what goes on there, and then I'll send you home hopefully happier and more informed. So why study plasma? So if you look at the overall composition of the universe, only 4% of the universe is made or is composed of the matter known as baryonic matter. Okay, that's the matter of which we are composed, of which stars are composed. All of that accounts for, again, only 4% of the universe. The other 96% is divided into a 23% of dark matter and about 2/3 dark energy, neither of which we know about. We've been actually, I spent 3 months in Italy under a mountain, 10,000 feet of rock, waiting for dark matter to come and hit us, and it never did. So, but at least I got to have the coffee and the wine and the fresh bread. That was always a very, very nice thing. Science is such a hard thing to do, so, you know. So why? Again, 4% of the universe is composed of baryonic matter, but 99% of that exists in the form of plasma. And so if you're not looking at plasmas, you're not getting the whole picture. So again, we've always learned that there were 3 states of matter: solid, liquid, gas. But it really is solid, liquid, gas, and plasma. Now, a plasma, it would be virtually indistinguishable from a gas until you threw in a magnetic field or an electric field. Once you throw those things in, then the particles start dancing around, and it gets really exciting, as opposed to the gas that just kind of sits there. So plasmas are a lot cooler, I think. But what happens is, if you know about the environments, like for the Earth or some of the gas giants, these things are giant spinning balls of gas, and they generate very intense magnetic fields. And so in that kind of an environment, the plasma is going to give you a lot of information. And if you don't have a plasma instrument, you are not going to get any information about the kinetic or dynamics of the entire system. So you've got to be able to study those plasmas. And if you were a plasma physicist, this figure right now would make you go fetal. The whole idea that I'm trying to get across here is that plasmas are everywhere. We've got them in the magnetosphere. This is the area surrounding the Earth. We have it in the solar wind. The solar wind is actually constantly bombarding us. The solar corona, which has a temperature of about 1 million degrees. Fusion machines that we are currently using, tokamak reactors, that's what we've been trying to commit. What's the joke? The way it normally goes is we've been trying to commit fusion for about 30 years, and we're only about 30 years away, and I think that changes every 10 years or something like that. We're still trying to commit fusion. We can't do what the sun does, but all of those things involve plasmas. So in this cartoon, you are seeing kind of like this fizzy stuff coming from upstream of the Earth. Now, this is the solar wind. The solar wind is a plasma which is constantly buffeting us. Okay, but thankfully, the Earth has a magnetic field. If we didn't, then that lovely plasma would come and strip away all of our atmosphere. But what happens is the yellow line represents something called the bow shock. This solar wind is a supersonic wind in the environment. It flies up and it hits a magnetic field. Now, like I was telling you, when charged particles, when a plasma hits a magnetic field, it starts doing some interesting things. It starts to gyrate, starts to make circular paths. So it goes from being a supersonic wind, hitting this obstacle, and then slowing down. But all that energy has to go somewhere, so it actually goes into heat. Okay, so it actually starts to heat up the environment. And what you're seeing are, in the region up front, what's known as magnetic reconnection, okay? The sun is a spinning ball of plasma. It also has a magnetic field. And so what'll happen is the magnetic field from the sun will abut with the Earth's magnetic field, and if they're in the right orientation, they will recombine and drape around. As that occurs, those lines will drape around to the back, and if you notice, in this region here, you're going to see these two lines come together. So these are two magnetic field lines of the Earth's magnetic field. They recombine in the back. And if you notice, there's little lights that are flashing and precipitating into the atmosphere. Those are what we know are better known as the aurora borealis. See, magnetic field lines are like rubber bands. You can pull them and stress them, but if you pull and stress a rubber band too much, you're going to hurt your fingertips, okay? Same principle applies here. You start twisting up a magnetic field, it just breaks, and all that energy has to go somewhere, so it goes into particle acceleration. It actually takes the electrons and accelerates them so that they come and bombard the atmosphere. So, and this is just another cartoon to give you an idea of what is going on, okay? The red line would be a magnetic field line from the sun, the blue line, a magnetic field line from the Earth. They combine and they move apart. But in doing so, they slingshot particles. They impart energy to the particles. Again, just an idea of what's going on. Again, here's the bow shock. Here's the reconnection point. Again, in the back here. And that bow shock, what's happening at the bow shock is everything's coming to equilibrium. All of these particles are kind of getting mussed about. And so, again, they have to go somewhere, and the magnetic field lines pretty much dictate that. One more time. Of course, if there was a dead horse in the room, I'd probably be beating it right now. But if you get the idea here, yes, there is reconnection going on, and it all goes into the way particles behave. It even occurs on the surface of the sun. And, I'm sure everyone's heard that we go through solar cycles, right? We have a 22-year solar cycle. And what is happening is that the magnetic field lines at the equator of the sun actually spin faster, or they rotate faster than the magnetic field lines at the poles. And so you end up getting the situation where the equator begins to lap the magnetic field lines at the poles. And of course, you're going to have situations where you can have anti-aligned magnetic field lines, and you have reconnection at those points. That's what's causing your sunspots. And notice it intensifies as the solar cycle proceeds along, and it comes to a point where you basically reset and you start all over again. And you usually at that point you actually flip the orientation of the field as well. So again, very involved process. Again, I stress that evidence of magnetic reconnection can be easily seen as aurora. Now, I think you should be able to see aurora a few times a year up here, right? You guys are lucky. See, in Texas, we don't see it much. But I remember one time I was 18 years old. This is back when I had joined the Army, and I was a fresh young infantryman. And so we got to play what's known as opposing force, Op4. And we were playing opposing force against the 7th Infantry Division or something like that. And we were supposed to, and I quote unquote this, die in place. We were supposed to pretend like we were ambushing them. And, they, of course, die in some, grandiose manner. And okay, good job, well done. They never showed up. They never showed up, so we just did the rucksack flop and just sat there. Well, I'm sitting there, and I look up in the sky, and sure enough, shimmering back and forth are blues, greens, and yellows. And I remember I was like, no way. And all my friends were like, oh, hey, Gomez, what is that? I'm like, well, that's the aurora borealis. The only problem is that you shouldn't see them in northern Florida. And so, you know, I was sure that this was occurring, but, you know, again, I think it was an E3 at the time, and when you're in the Army, you really don't have time to go and research things. So I had to go and research. I had to go do back research. And sure enough, on March 6th of 1989, there was a huge X-class solar flare that had erupted. And, you know, it takes a while. These particles don't travel. They travel at about 400 to 600 kilometers per second, which is fast, but it's not the speed of light. You know, it takes a photon 8 minutes to go from the sun to the earth. These things took about a week. But sure enough, on March the 13th of 1989, there was a huge X-class solar flare. It knocked out part of the power grid in Canada, and it lit up the sky like a Christmas tree, and it was really an amazing thing to see. And I thought it was like a once-in-a-lifetime experience, but apparently about maybe 2 or 3 years ago, it happened in Alabama. I've never seen them in Texas, but you never know. We'll see. Whenever you're doing all sky cameras, and this is the big thing with Aurora, you got to take it in its entirety. The only problem is, as most astronomers will tell you, there's something known as light pollution. So, you know, no matter what, I mean, you can have, you know, a tower of lights, or you can have a car driving by. Any type of light introduced is always going to mess things up. So you've got to find other ways to look at things. So again, I was telling you, we are trying to look at plasmas. I'm not trying to look at the lights, even though they're pretty. I get more information from the plasma. So how do I do it? Well, you have to understand that the plasma is speaking a different language than you. And so in doing so, you also have to realize that there are other things that you have to measure. We know that they are under the influence of magnetic fields, so we measure those. We measure electric fields. We sometimes want to look at what are known as energetic neutrals, which are particles that are not charged, but they're still flying with a tremendous amount of kinetic energy, so you've got to be able to see those as well. And then look in electromagnetic radiation. So you also want to make measurements in situ. In other words, you want to measure in the environment. Okay, it's kind of like being in the reality show and then watching the reality show. Okay, we'd rather go and put the instrument in the reality show and make the measurement there. So how do you do this? Well, you build instruments, you mount them on a spacecraft, and you launch them into orbit, and you make sure that NASA pays you to do it. That's the important part, okay? So the suite that I worked on, or the mission I currently work on, is known as MMS. It's the Magnetospheric Multiscale Mission. It was launched March 12th of 2015, and it was a 2-year mission. We have actually already completed our primary mission. The whole part of the mission was to look at magnetic reconnection instances, both on the day side, on where the side where the sun is, and on the night side. The first part involved doing day side measurements. Second part involved doing night side measurements, and we've actually successfully completed it. And thankfully, knock on wood, NASA has decided to fund us once more. So we'll continue doing that. It's 4 spacecraft that are flying together in a tetrahedral constellation. And the reason why you do that is because if you have two spacecraft, or one spacecraft, you can measure a point of data. 2 spacecraft allow you to measure a line of data. 3 spacecraft allow you to measure a plane of data. But if you have 4, now you can look at gradients in 3 dimensions. So that's the whole reason why we put 4 instruments up. We've got 100 sensors on 4 spacecraft. And it's truly a multinational collaboration. We've got people from Spain, Portugal, China, Japan, just about any country you can think of, France. Okay, so, and it's nice to work with people who are, come from across the world, because, they always give you nice little tidbits on what to eat when you're in their country. Good stuff to know. So, this is video of the launch. And wonder if we have the
T-minus 10, 9.
Okay, we may or may not have sound on this.
7, 6, 5. Go for main engine start. 3,
The interesting
2,
thing is, you were watching this occur. When this was occurring, I was there with my daughter, who was, I believe, 14 at the time. And so it was great to be able to watch this go up, but it's even better to share it with your kid. And I absolutely adored that. But while you're there, you realize, wow, something that I've been working on, something that I've touched, something that it's a part of history is actually going into space. This is really awesome. But the other half of you is saying, wow, everything that I've worked on for the past 5 years is on nothing more than a controlled explosion. Please don't blow. So again, this is your moment of clarity. You know, again, a kind of an emotional time because, you know, you pour your heart into working on a project like this. I got my PhD in 2011. I was actually an old PhD. I got my PhD at the right, I say old, middle age of 41 years old. You know, I'd already had a full life beforehand, but I remember my PhD, at the end of my PhD defense, it was kind of anticlimactic. It was like, all right, good job, Roman. Now get your butt in the lab because it's time to calibrate the instruments. That was my advisor, Dave, and I adored the man. The spacecraft are very simple. Notice they don't look anything like the old Buck Rogers, or they're not TIE fighters or X-Wings or anything like that, okay? It's a spinning spacecraft. These things are spinning at a rate of, 1 revolution every 20 seconds. And the way our instrument is set, this is HPCA right here, the way our instrument is set up is it looks at both ways and it just spins. And we just change voltages so we can look at energies. And we do that every 625 milliseconds. So we can scan an energy range from 1 electron volt to 40,000 electron volts. And for comparison, the average speed or the average energy of a particle in this room is about 1/40th of an electron volt. So we're not measuring that low, but we're still measuring pretty low. But we go from 1 to 40,000, in other words, 4 decades in 625 milliseconds. And we're not even the fastest instrument on the spacecraft. There's another one that does it in 30 milliseconds. So this is one of my beautiful children, MMS-HPCA. It is an instrument that is designed to measure, as I said, energy, but it's also measuring composition. There's always a question is, yes, we know the plasma is made of charged particles, but what type of charged particles are participating? Is it all hydrogen? Is it helium? Is it oxygen in there? Is there neon? What is it made of? If you just included this front part here, that would allow you to measure just all the counts in the plasma. But we want to go one better. We actually want to know what is in it. So this thing simultaneously measures energy and composition. And here's the trick. When you, like I told you earlier, or if you saw in the slide, when you're out there in the magnetosphere and out in the solar wind, almost everything is hydrogen. Okay? Hydrogen is the most widespread, ubiquitous form of atomic matter in the universe. Whoopity-doo. Okay? I know it's out there, but I also want to know what else is out there. The problem is when you have that much hydrogen, it can completely overrun your signal capability. And so what you have to do is find a way to bring it down. Okay, so going from here to here, it's 4 orders of magnitude, or about a factor of 10,000. So it's hard to measure, you know, things that are down in this area when you've got atoms that are of this level of composition. So you've got to find a way to rectify that. And so that's one of the things we had to develop. How do you knock this thing down? And so our brilliant trick, actually it was a brilliant trick of my boss's boss, his name is Jim Birch. He said, well, why don't we throw radio frequency in there? Why don't we, normally these things work with a DC voltage. I'm boring you to tears, I'm sorry, I have to talk voltages, I'm sorry. We normally run these things with a DC voltage, but we said, well, what happens if you throw an oscillating signal on there? Now, again, these are charged particles, so if you throw an oscillating signal on there, you can change their path. And so the idea here was, if you're very light, like a proton, we can deflect your path enough that we can completely knock you out of the stream. But if you're more massive, you kind of oscillate, but you even out on the path. And so we have found a way to completely, we can completely remove hydrogen from our signal and only allow heavy ions through. Now, we don't want to completely remove hydrogen. We want to be able to still see it. We just want to bring it down a notch so that we can see everything. And so that was the whole idea with this radio frequency. Again, this is kind of an idea to get you to go, if you notice, again, hydrogen is this line here. It's being deflected the most, whereas oxygen, on the other hand, remains close. Now, our plate spacing is about 1 centimeter, so it's between those two. So whatever goes outside those lines is getting removed. Whatever's staying inside is maintained. And so that's how we get around this problem where we're just inundated with protons. Now, to make sure that it behaves, you don't just build the instrument and throw it out there. Okay, it's kind of like, again, raising kids. You don't just like have them and then say, okay, go do whatever you're going to do. Okay, you actually have to raise your kids. So in that same token, when you make a plasma instrument, you have to know how it's going to behave. And so calibration is the name of the game. This is what I actually ended up doing after I got my PhD. Again, this is what I ended up doing for the 4 years leading up to the launch. I spent 16-hour days in the lab and, made sure that I was told to do this series of tests and, you get that done and, okay, you go home and, eat the cold dinner and then, wake up at 3 o'clock in the morning to go in and, it got to be somewhat repetitive, but the payoff was nice, watching the launch. Now, again, I told you that we measured plasmas from 1 electron volt to 40,000 electron volts. This EPIC system is capable of making plasmas down as low as 98 electron volts and go up to 40,000 electron volts. It's kind of hard to hit that lower energy because the Earth's magnetic field actually will cause particles to curve. And so you're kind of like, oh, how am I going to get this thing to work? And we said, well, sometimes you just have to stick with what you can get and then extrapolate down. I do point out, though, that it is absolutely my favorite toy. Okay? This is, when I was a kid, reading up in comic books, we're always, reading about these weapons like, particle projection cannons and all. This is my personal particle projection cannon, okay? I make a space plasma and I fire it at my instrument, okay? Again, that's not the only part. You actually have to be able to mimic a space environment. So this vacuum chamber, we can get our pressures down to 100 billion times lower than what we were experiencing right now. Basically, you want to make sure that you have a nice clean vacuum because when you start putting high voltage on these things, if you have any kind of air in there, they'll arc. And every electronic component works on the principle of magic smoke, right? So you apply voltage and hopefully the magic smoke doesn't come out. If the magic smoke comes out, then it no longer works anymore, okay? And then you have to tell the taxpayer that, congratulations, you're now flying a glorified paperweight. So that's something you definitely don't want to do. So we're always trying to be careful. This is our command and control system. This is the coffin. And this right here is our ion optical source. This is the actual part of the ray gun, if you will. And we use this is a field called ion optics. So kind of like you have your lenses that focus light, we use electric fields to focus charged particles. And we can do all kinds of things with them. We can rotate their moments, we can focus them, we can defocus them. And with this, we are able to provide either a single species beam, a multiple species beam. It's nice and expanded. This thing right here is called a beam expander. Its analog would be what's known as a converging lens. So, when you were a kid, and you got the magnifying glass, and you either use it to light fireworks or burn ants or burn your friend's leg or something like that. Guys know you've done that. It works in reverse. You put the source at the focal point, and it will make a nice cylindrical beam out to infinity. Now, luckily in my lab, all I need is 1.5 meters is infinity, so it works out just nice. This is what the RF does. This is if you operate the instrument without the radio frequency, then you get a full transmission of oxygen, or hydrogen. If you turn on the radio frequency, it actually cuts this passband in half, and it reduces it by about a factor of 100. Now, this is at just one setting. Again, we can reduce it by a factor of 1,000, but it's always nice to have something so you have something to correct. This is a diagram of our primary mission. Again, this is the Yellow here is showing the orbit of the instrument. This is it coming on the day side. And notice this part right here is the bow shock. What is happening there is there are some points when we are actually outside of the bow shock. We're actually in the pristine solar wind. And I'll talk about that in just a bit because that's what I'm interested in right now and what I'm working on. This is where we actually go into the tail. We've already completed the primary mission. We've sampled quite a bit of space here. So much so that when you actually do your work, this is the tough part of being a scientist, okay? I like working in the lab. I really love working in the lab, and I like helping my friends working in the lab. I hate writing papers, okay? It's tough sometimes, you know. It's easy to get writer's block. And again, I think this is one of the trials and travails of being a scientist, but it's your responsibility. You know, when you make a discovery or you make an observation, it is your responsibility not only to report something like that to the scientific community, but also to try to make it available and digestible to the community at large. They need to be able to know what you're doing. So what we did here, and again, I'm a plasma guy, so there's a little bit of interpretive art in this. But what we were looking at in this case was a situation when we were actually on the side of the Earth. We weren't out in front. And again, what we're looking for are signatures of magnetic reconnection. So charged particle acceleration. We're looking for flares and energy. And so what we're looking at here is how the magnetic field changes. That's what the top portion is. We are also looking for signatures of particle acceleration, high energy particle acceleration. You believe me, I've been looking at these things for 2 years, and I sometimes wonder, am I really seeing what I'm seeing? Yeah, so I can see right now, it's like, yeah, what is this guy talking about? This is actually snake oil. But again, what we're looking at, again, is charged particle signatures and acceleration. And we look for when we actually have on our sensors, we look at 360 degrees on that little bit. As that thing is moving around, we see charged particle acceleration either from above or below. And so what we saw in this situation was that we originally saw acceleration from below the spacecraft, saw acceleration above the spacecraft, and then we saw it occur at 2 points, and then we saw it occur at a single point again. So remember that the spacecraft is traveling in a nice, placid path. Okay, it's not doing any kind of oscillation or jumbling around. If you did that, you'd break something and you'd know it. Okay, so what could be moving? Why do we see these signatures come from above and below? And what the simple answer is that, one, it's the line that's moving. Okay, this reconnection line is actually moving back and forth. This is the crossover region right here. Okay, now what it's showing is this relative motion. This is the relative motion, okay? What's happening is you have a reconnection site occurring below you, then all of a sudden it moves above you, and at this point we're actually seeing 2 reconnection sites. One of them is persistent. It stays, it's constantly reconnecting, but you're seeing another site that is also erupting as well, and it's intermittent. And so our current insights into magnetic reconnection, what is it going on, is, again, it seems to be an ongoing process, that it's constantly ongoing. Magnetic reconnection would be the primary means by which you take energy and transfer it from the solar environment into the Earth's environment. Okay, it's not radiant energy. Believe it or not, it would be reconnection. It's particle acceleration. It's injecting particles into the currents. Okay. Again, in addition to the persistent component, though, there are intermittent cases, kind of like what we see with the sun, right? As the equatorial portion of the magnetic field starts to spin up, you get more and more instances of reconnection. And so it seemed to be cyclical. Now, there are questions. What is the total rate of energy transfer? We're still trying to answer that. Another question is, how does the solar cycle affect this? And moreover, lastly, How does the plasma affect the rate? That's something we're still looking at. So hopefully you are enlightened a little bit more about magnetic reconnection. My current research, though, so what ends up happening as a scientist is you sometimes have to find your niche. And when you're working on a project where everybody is doing magnetic reconnection, you're like, okay, well, I need to do something else. I got to find a way to differentiate myself. I don't want to be reinventing the wheel. So I was telling you about that, the times when the spacecraft is actually moving outside of the bow shock, when we're in the pristine solar wind. This is what interests me. So as we're moving through the Milky Way, okay, the sun is orbiting at about 225 kilometers per second. We have the interstellar wind, okay, the interstellar medium, which sits outside of that. The sun's solar wind actually moves out, it propagates outward to a point where it comes into contact with the interstellar medium and forms a termination shock. And how do we know that exists? Well, guess what? Voyager 1 and Voyager 2 have both crossed it, and we've made a measurement of that. The bow shock here may or may not exist, but we're pretty sure that the heliosphere does. Because what happens is, as this starts to slow down, the same thing occurs as with the solar wind. That supersonic solar wind slows down when it comes into contact with the interstellar medium. But the big question is, what is the composition of the interstellar medium? Now, I mean, it's one thing to measure the plasmas near the Earth, but it's another thing to measure the plasmas way out in space. Okay, if you remember, how long did it take the Voyager probes to get out there? Quite some time. Okay, I think they were launched back in the 70s, if I'm not mistaken. Okay, so it took quite some time to get out there. But you want to be able to make actual measurements. Okay, most of the knowledge that we have of the environment outside in the near interstellar medium have to do with ultraviolet measurements mostly, or any type of spectroscopic measurements. But again, you want to be able to do direct measurements, but it's hard to get an instrument out there. So what do? You find a way to bring the particles to you. And again, that's what I'm working on right now. So these particles come in from outside the solar system, outside the termination shock. The trick is that they are not charged when they enter. When they enter, they are neutral. If they were charged, then they would be bounced back out of the solar wind. But in this case, they will move in, they propagate, and again, retaining all of their information as far as velocity is concerned, direction. And as they propagate in, they come near the Earth, okay, at this point. When they get near the Earth, there's a chance that they will be ionized. And if they are ionized, then my instrument can find them. And so that is actually what I'm doing these days. I'm looking for these interstellar ions as they propagate into the solar system. And so far, I have found hydrogen and helium, found a little bit of doubly charged oxygen. And again, this is just a time of flight mass spectrum. This is the second part. Remember, I told you I can look in energy. So looking across this way, this is energy, or each step above is energy this way. And as I move out, this is time of flight. So I can find I can not only measure them in energy, but I also measure them in mass, and I can tell you what they are. Okay, so now that I've bored you sufficiently with that, I want to just close in talking about where I work. So Southwest Research Institute is one of the oldest not-for-profit research facilities on the face of the earth. Okay, it was founded in 1947. We recently celebrated our 70th anniversary. We have 9 technical divisions ranging from applied physics all the way down to space science and engineering. We have 2 divisions in space physics also. We have one in San Antonio, and we have one in Boulder, Colorado. Boulder, Colorado usually does mostly modeling. The one in San Antonio, we do all the instrument building, and we actually do a bit of modeling there, but again, more hardware type research. We do space physics, ultraviolet spectroscopy, spaceborne mass spectrometers, which is part of the stuff that we work on there. We've got observational astrophysics, planetary geophysics and geochemistry, and last but definitely not least, and one of the biggest pushes that we have is in astrobiology. So if you guys watch, Neil deGrasse Tyson is a big guy on this one, but you know, one of the hot spots in the solar system is Europa. Okay, Europa is a moon of Jupiter. It has a 1,000 kilometer thick ice sheet. And from all measurements, it seems that there's actually a liquid ocean, okay, underneath all that ice. So one of the things that we always look at here on Earth are types of organisms known as extremophiles. So things like water, what are known as tardigrades, are also known as water bears. There's also the worms that live near the hot vents at the bottom of the ocean. The idea is if there is a place where life can exist, water being one of those things that we know of, that there just might be a chance that we find life there. And so again, astrobiology is a relatively new field, but it's something that we've actively jumped in on. I know that it's something that interests quite a few people in the field, including some of the people here at Southwest Oregon Community College. As far as Division 15's activities, it's been crazy. I started in 2007. My boss, though, and who was also my thesis advisor, he was the guy who started the Cassini plasma spectroscopy investigation. So again, that was launched in 1997. It arrived at Jupiter in 2004, and if you've read the news, we bid a very sad farewell to a monolith of science. There were so many scientific discoveries made just for Cassini caps, and for Cassini, the Cassini mission itself. And so, and actually, one of my friends who worked on that quite a bit is actually in the audience right now. It was a sad day, but you know, we realized that we have to continue moving, and that's exactly what we've done. So far, we have the image. We've got Mars Express, Rosetta. If you remember Rosetta, that was another mission that I worked with. That was the one that fired was it the Philae lander onto the asteroid. That was a hair-raising moment because, you know, it took an hour for us to actually verify whether or not the thing had actually landed and was able to do measurements. Deep Impact was a mission to an asteroid, again, MMS Smart. We also have, recently we had the Cygnus mission, which was launched from an aircraft, and that is responsible for tracking hurricane activity. So we are a very involved research conglomerate, and you know, we're growing by leaps and bounds, which is one of the reasons why I always try to make sure that I come out and talk to the public, because, you know, like Ron was saying, I took a very roundabout path to becoming a scientist. So one of the things I always do is go out there and talk and say, hey, you know, this is a field that you can get into. There's room for everybody. You just have to have the desire to do so. There at Southwest Research, we have 149 physics, a lot of chemical and chemistry engineering, computer science. It's a multidisciplinary research facility. So there's a lot of room to grow and a lot of room to kind of tentacle out, if you will. So, in closing, why do we do what we do? Why do we do science? I mean, it's to learn more about the world, but it is fun. Okay, I have been a scientist now, a full-fledged scientist, I guess, working at Southwest Research since 2007. I finished my PhD while working there. So in the 10 years that I have been working there, I can honestly tell you that I've never worked a day in my life because it's a good time. It's fun. I get to work with smart people, and it kind of rubs off on you sometimes. And that's why I say it's a great place to work without, or make a living without working, because again, I don't work. And for the endorsements, I throw this in as a joke. One of the things I've always done is I work with these vacuum systems, and in order to get them to work correctly, you have to wrap them in foil and bake them for like 24 hours. So I joked with Dr. Coiner when we were in grad school. I said, you know, one of these days, I'm going to get an endorsement with Reynolds wrap. And I think the slogan should be, if an astrophysicist is using it, shouldn't you too? So, again, ultimately, it's about finding your purpose. It's about finding your path. This is one thing that I always hold on to. It's one of my favorite pieces of poetry. It's the answer to "Oh me, oh life." And it states that, why do we do what we do? The answer is that you are here, that life exists and identity, that the powerful play goes on, and you may contribute a verse. And I'm trying to contribute as many verses as I can, and I hope that you, if you have the opportunity, take that chance as well. And I thank you very much.
So we got time for a couple questions, and I'm going to toss this to you.
I was wondering if, from your viewpoint, you could comment on what's going on with the current solar cycle being somewhat of a dud from your.
Yeah, well, you know, that's funny. That was one of the things that kind of concerned us when we were doing when we were initially working on the magnetic reconnection. How is that going to affect us? You know, as we know from previous measurements, the solar cycle is not something that's constant, right? You know, you can have lows in the solar cycle. Case in point was at the Maunder minimum, which I believe occurred during the 1600s or something like that, where you had little to no sunspot activity. And so, you know, there's still so much about the sun that we don't know, which is one of the reasons why we're also actively participating on solar probe, on the solar probe instrument, where we're actually supposed to travel closer to the sun than we've ever traveled before. We're trying to measure the corona and things like that. So, yeah, there's, again, when you do research, what is it? One answer leads to 1,000 other questions. And to tell you the truth, it's actually, for my research and from my standpoint, I like it when the sun is at its low point in the solar cycle, because what ends up happening is I don't have to worry about the solar radiation pushing away the protons from way off. So, again, I'll keep you posted on what we find.
I was going to ask about any solar flares, making that last sentence that you just talked about. What affected solar flares in the sense of the bow wave and things like that for your instrumentation?
That is a really good question. So solar radiation is always a problem, right? You have to be careful with energetic particles, because those things they can actually penetrate your instrument and wreak havoc with your detectors. So that's one thing that we're always on the lookout for. One of the problems that we also run into is the radiation belts of the Earth. When we're actually going into them, we actually shut down. That being said, we really haven't had too many problems with solar flares. We actually will see an enhanced signal, but nothing that would wreak havoc with our sensors. I know for a fact, though, that my friends who are doing research with Juno, they have to be quite worried. The second largest object in the solar system is the magnetosphere of Jupiter. And so what you have there is a case where you have a natural particle accelerator. And so when they first launched the spacecraft around Jupiter, one of the big issues was, how long are we going to be able to operate before we have one of those nice energetic particles going through and, make the magic smoke leave your electronics, right? So these are the things that we have to worry about quite a bit, but not so much with solar flares, interestingly enough. We're far enough away from the sun that they kind of dissipate by the time they get here.
You said that you had other devices that you shot in space, and one of them were being that you had shot one to Mars. I was curious what kind of discoveries we made on Mars.
Oh, okay, and you just touched on that hurt. No. So I've worked mostly with MMS. My initial shot at my doctoral thesis was going to be a mission to Mars. It was going to be called TGE, the Great Escape. And so I remember we went toe-to-toe with NASA Goddard. And we were the last two left for selection. And I was working with an instrument that was very similar to the one that I'm working with now, but it was a little bit superior in the mass resolution. When you bid against NASA, you have to sometimes understand that you're bidding against people who are also trying to keep their people employed, right? And so we had a superior instrument sweep of our mass spectrometer and our plasma instrument, but we got dinged on our delivery vehicle, is what it was. And so I remember I went home to my wife, and she asked, that great question, how was work today, honey? So I kind of just hung my head and I said, sweetheart, growing up, all I ever wanted to do was work for NASA, and all I want to do now is whoop their butt whenever I get a chance. So don't ever let anyone tell you that scientists aren't competitive, because we can be really competitive.
So I know that Roman would be happy to stick around and answer some questions from you if you still have them. I'd like to thank you all for coming out.
Thank you so much.
I'd like to thank the Umpqua Community College Geology Club for making the trek over from Roseburg today and touring the area a little bit and showing up this evening. If you are interested in finding out more about the Foundation's $1 Million Match, our executive director of the Foundation will be out in the lobby afterwards. And if you didn't sign the sheets, please take a moment to do so, because attendance helps keep this thing going, believe it or not. I'd sincerely like to thank both Dr. Coiner as well as Dr. Gomez and Roman for making time. Making time not only for the talk this evening, but also talking to some students on campus about STEM careers, as well as the Veterans Club yesterday as well. So it's been a pleasure having you. Thank you all for coming out. Hope to see you in January.